This lesson will cover combining transformations. The learning goal is to apply a combination of transformations on the equation of a function and its graph. Your success criteria is you can describe the transformations of a function based on the equation of its graph, and you can create a graph of a transformed function. So we've discussed translations, reflections, stretches, and compressions, and what a function can have is equal to transformations. It's more common for a given function to have a combination of transformations. So we need to know what all of the transformations are and how they act and what variables they're represented by in the general equation of a function. So if we have y equals a times f of k times x minus d, all brackets plus c, a, as we saw before, is the vertical transformation, or transformation is the stretch, compression, or reflection. And then k inside the bracket, that is our horizontal transformation. D inside the bracket, that is our horizontal translation. And then C on the very end, this is our vertical translation. Now, it is very, very, very important that when transforming curves, you need to implement changes from left to right. So as you read, you work left to right. It's also important that the k value is factored out from d value. So notice in the general equation here, see how k is separated from x minus d by a bracket? If you have, for instance, let's say you have f of 2x plus 3, let's room over here. So we have f of 2x plus 3. You'd have to factor out that 2, and it become 2 bracket x plus 3 over 2. So if you do have a coefficient of x you need to factor out, it does affect the horizontal translation, so just be very much aware of that. So remember that in the above notation, f is just notation. In a question that's replaced by the quadratic, it's a square, it can be a root, it can be absolute value, it can be a reciprocal, and that will tell you the shape of the parent function. So sketching transfer function will use all the methods from the individual transformations. Let's look at 2 examples here. So the first is we're going to state the transformations that occurred from the parent function, and then sketch both the parent function and a given curve. So here, I already can see that I have an absolute value function. So now my parent function is y equals the absolute value of x. And I need to state my transformations here. I have a vertical reflection from the negatives. Here's my vertical reflection. So I have a vertical reflection. I have a vertical translation down 1. And then I have this bracket here. Remember, I do not want a coefficient of x. I need to factor it out. So this becomes, instead, negative absolute value of 2, x plus 3. I'm factoring that 2 out of 2x plus 3. And then that's the equation I'm using. So I have a horizontal. Looks like I have a compression. Remember that a whole number here greater than 1. That is a compression for horizontal transformation, so horizontal compression by 2. I should say a factor 2, but it's right 2 right there. And then horizontal translation 3 to the left. Okay, so I have my transformations. Let's start with my parent function first. So let's do the parent function in blue. So let's get my table of values out. Let's get my key points down. I'm going to have negative 2, negative 1, 0, 1, and 2. And absolute value of each of these x values is 2, 1, 0, 1, and 2. So let's plot this on our graph. So here we have 0, 0. Here we have 1, 1, 2, 2, negative 1, 2, and negative 2, 2. So get our lines and arrows. Remember, we always need these arrows here to show that we're going off in infinity both directions. Now let's do our transform function. So for the transform function, this is what we want to do. We want to take these transformations here. We're going to set up a second table of values. And we have our x value and we have our y value. Now, this x and this y, these are the original key points of our parent function. So let's look at these transformations. We have a vertical reflection, so that means we have a negative y value, and it's a translation of down 1. So we're going to subtract 1 from a y value. For our horizontal transformations, we have a compression by 2, so we're going to divide x by 2. Let's do this, x over 2, and then we need to go left 3, so we have to subtract 3. So we're going to take all of these x values, plug them into that x. We're going to take all of these y values and plug them into that y. So that'll give us our new points. Okay, so negative 2 into x, negative 2 divided by 2, that's negative 1. Subtracting 3, that gives us negative 4. And we have negative 1 into x here, so negative 1 divided by 2 is negative a half, minus 3. It's about negative 3.5. And then 0 is just, well, 0. And then minus 3 is 3. And we can start to see a pattern here already. It's minus 3. It looks like we're going down, up, actually, by 0.5. So next one's going to be negative 2.5. And then we have negative 2. Now you can plug 1 and 2 into the equation just to confirm. But if you do start to see a pattern, which you normally will when you're doing this stuff, you can skip ahead. So let's take our y values, plug them in. So the nice thing about this is we have 2 of the same y values, so we only have to do 3 here. So 2 into negative y minus 1, that's negative 2 minus 1, that's negative 3. And then 1 into negative y, that's negative 1 minus 1, that's negative 2. And then we have negative 1. And then we have the same values above, negative 2 and negative 3, because we have 1 and 2 again. So these are my transformed points. Let's plot these. So we have negative 4... negative 3. We have negative 3.5, negative 2. We have negative 3, negative 1. And then we have our points repeating again. And we can connect our lines. And then this is g of x. So that is our transform function by taking our parent function, taking its points, taking our transformations and plugging them into a new table of values that will allow us to grab those transformations. Now let's look at our second example here. In this case, we already have a graph. And we have the transformations acting on said graph. Our function f has 1/2 f of negative 2 of x minus 2. So let's state these transformations here. It looks like we have a vertical compression by a factor of 2, let's say by 2. We have a vertical translation two down. And we have in the bracket here negative 2. So that's a horizontal reflection. Technically, it's a reflection on the y-axis. So I'll just write horizontal compression first. So horizontal compression by a factor of 2. And then we have a reflection on the y-axis. That's the proper way to say reflection, not horizontal reflection. So I'll use the proper notation here. Now I have the graph already, so I could take each point and apply these transformations to it, or we can take a set of points and plot them in. There's 2 ways you can do this. So one, I'll show you how you can do it just using the points. When you're applying transformations, it is very, 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 very important that you apply stretches, compressions, reflections first. Translations are always going to occur last, because if you look up above here when we did table of values, you follow bed mass. I'm plugging in the parent function points in, and the compressions and reflections happen first. So always apply those to points first. So I'll just do 1 point here, and then I'll show you another method here. So I'm going to take random points. I'll just take the leftmost point. So here we are. This point needs to be vertically compressed by 2. Where the 2 there? So vertically compressed by 2 places it right here. And then I have a horizontal compression by 2. So that puts us, this is 3, so 1.5. So it puts us about right here. And then a reflection on the y-axis. So we have to go to the y-axis and reflect. So this point is here, and then we have to translate 2 down. So 1, 2. So this point ends up over here. And you can kind of see it is a lot of steps we have to do for each point. Yes, we can definitely do that, and for some people that's easy to do. But we can also set up a series of points instead. So I can take these coordinates here, grab the coordinates of all my points here. So I have -3, -1, the one we just used. We have -2 and 2, that's right here. And then we have 0, 2. And then we have 1, 0. And then we have 3, 8, 2. And we can apply these transformations to these coordinates. So what's going to happen is as we move over, our coordinates are going to change by becoming -1/2 of x and y over 2 minus 2. So we can plug all these coordinates into this new system here to grab our transformed coordinates. So -3 into x, that's -1/2, that's 1.5. And then we have, actually let's change colors for this. Let's go to blue here. So we had 1.5. And then we're plugging -1 into y here, so that's -1/2 minus 2, that's -2.5. And we can just go through and plug all these points into our kind of formulas here to grab our transformed points. So what I'm doing is I'm plugging, for instance here I did 0 into x, that's 0, 2 into y here, y over 2 is 1, minus 2 is -1. So I'm just plugging these x and y values into this formula to grab my new points. Here I have -0.5, and then I have -2, and finally I have -1.5 and -1. So we already have one of our points, and then we have 1, -1. We have 0, -1. We have -0.5, -2. And then we have -1.5, -1. And you can kind of see the same shape we had before here. It's just being reflected and severely compressed vertically and horizontally. So when you do transformations or combination transformations, you can take individual points, apply the transformations to each point. You can definitely do that. And the nice thing about that is if you do that, because you know the shapes of these functions, you can just do a few points and then create the function based off of that. My recommendation is make a table of values and then apply the transformations to the old points, or you can do a series of coordinates like this and create new transform coordinates using these formulas, which is basically using the table of values method. It's just kind of written in a different way. So all of these work, whichever one you prefer, they'll all give you the transformed functions.